The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. This is Elisa Baum, and I'm GridGain Systems Director of Product Marketing. We'll begin in just a moment, but first I'd like to conduct a bit of housekeeping. First, could you please raise your hand using the hand icon located in the GoToWebinar control panel to let me know if you can hear me? And let me take a look. Do I see hands? Can everyone hear me? Okay, please raise your hand if you can hear me. Thank you. Okay, great. I was a little bit worried there for a second. All right. Next, during this question, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we will take time to answer as many questions as possible. And in addition, I'll make sure that everyone gets a recording of this webinar and the slides within 48 hours after it ending. So I'd like to introduce today's speaker. It's Val Kolachenko. He is GridGain Systems lead architect, and he's also an Apache Ignite PMC member. He'll be presenting how to add speed and scale to SQL, support new data needs, and keep your RDBMS. So with that said, I'll turn the floor over to Val. Go ahead, Val.
Thanks, Elisa, and hello, everyone. Thanks for introduction. And yeah, my name is Val. I'm one of the architects at GridGain Systems. So I'm with GridGain Systems for several years already, and was working with different memory technologies. Today, I actually want to talk about how we can use this kind of in-memory distributed systems to accelerate SQL applications. So first of all, why do we even talk about this? Why do we even have this question in the first place? So there is a very typical challenge. So imagine you have an application that works with a lot of data, and the data is stored in a traditional RDBMS, traditional database system like Oracle or Postgres or MySQL or whatnot. So everything is working great. But at some point, you start hitting certain limits. So you have more data, you have much higher load on the system. And the only way to solve this issue with the traditional RDBMS is to scale up. It's essentially to increase the capacity of your servers, which is limited, first of all, so you cannot do this forever. And it also might be very expensive. So many companies, they face this challenge nowadays, and they are trying to find a solution for this, and they often find the solution in memory, in distributed memory systems. But at the same time, I mean, if you have a system that you can use to accelerate your application, you often do not want to get rid of your database, right? So for example, there are distributed memory databases like MemSQL, sorry, which you can use for this kind of to solve this kind of issues, but you will have to rip and replace. This is another challenge that exists here, because that's a bigger risk. That's a huge risk that many companies do not want to take, obviously, especially for mission critical applications. So today I want to talk about how you can use in-memory systems, and GridGain in particular, or Apache Ignite, to accelerate your SQL applications with minimal effort, without getting rid of your database. So so I would like to start with a short overview of the GridGain platform itself, so that you're aware of what we're doing here, and what our platform looks like, and what kind of goals we have, and how we achieve them. So this is like the high-level architecture of GridGain in-memory computing platform. So here we have several main components here. First of all, we have memory-centric storage, which is in the heart of the system. So this is essentially a highly scalable distributed data store, which provides good in-memory performance, and can be scaled out up to thousands of nodes and petabytes of data. So any memory storage that is used in a mission critical system needs persistence. So here we have a couple of options which are shown below on the bottom of the slides of the slide. So first option is third-party persistence, which means that we integrate with some other database or some other third-party storage for persistence. So this can be like RDBMS, this can be HDFS, NoSQL database. Apache Ignite is pretty flexible here, so we can integrate with any kind of storage. So that's actually what I want to focus on today. That's exactly how you would use GridGain in conjunction with your RDBMS, existing RDBMS, to make sure that you don't have to rip and replace. There is a second option though, which is a native persistence option. It comes out of the box within the Apache Ignite product. It is highly integrated with the memory store that we have, and it provides several advantages if we compare it to a third-party persistence. But this one obviously would require rip and replace and would require getting rid of your database in the first place. So I would touch this option a little bit later in the presentation, but I would want to keep focus on the first one where we keep the RDBMS in place. So and then on top of the storage, we have multiple different APIs that allow you to work with the data, to read the data, update the data, do some processing and whatnot. So we have different multiple APIs, which include SQL API, which is something I want to focus today as well. We also have key value APIs, like you can use it as a distributed hash map. Essentially, we have transactional support, fully ACID compliant transactions, which are currently supported for key value APIs, and support for SQL APIs. API is coming up. It's currently available as a beta version, and GA is coming soon. We also have Compute Engine. This is essentially the component that allows you to execute any arbitrary code on the server nodes exactly where the data is. So the computations can be collocated with the data for faster performance, and you can create any custom distributed processing using this component. You can also deploy services again on the server nodes where the data is, so that you can have certain APIs exposed to the client nodes, so that client nodes can use proxies to access those APIs, and the actual logic would be executed on the server side. There are also some streaming capabilities. You can stream data into Ignite. We have multiple connectors with other products. You can also stream the data from Ignite to some other system. So essentially, you can listen for updates that are happening in the cluster. And we even have a machine learning library built on top of the data storage and the compute engine that I mentioned before. So on top of those APIs, you will actually build the application that interacts with this data that you have in your memory-centric storage. The application would use one of those APIs or multiple APIs, so you can mix and match them. And in addition to that, we have several features that we provide as part of our Enterprise Edition, GridGain Enterprise Edition, that are shown on the right in blue. So these are like features that are usually needed for mission-critical applications. They provide better availability, like data center replication, for example, or data snapshots and recovery. There is also advanced security support, advanced monitoring and management support, and things like that. So this all is built on top of Apache Ignite and provided by GridGain as a part of Enterprise Edition. So as you probably noticed, we have those multiple APIs on top of the storage. So why we actually do that is one of the goals that we have is to create a platform that allows you to have the data in a single place, in a single system, that exposes multiple different APIs, so that you can execute different workloads on the data without moving it to some other system. So that's actually another challenge that is very, very typical. So you have like your operational database, like again Oracle, Postgres, or MySQL, or whatnot. But then you want to do some analytics, and you don't want to actually use the same database for analytics, because it's gonna be overloaded by those analytical queries. It's not actually suited for them. It's designed for different things, for different use cases. So the typical solution for that is to ETL the data like overnight, for example, from operational database to some data lake or data warehouse, and do analytics, machine learning, and this kind of stuff there in the warehouse. So this also works, but first of all, that's an additional complication. You need a second system to support this, and you also need to have this ETL process in place. And actually the biggest problem here is that it's not real time. So one of the requirements that we see more and more nowadays is to do everything in real time. Like essentially, when something is updated in the database, we want our analytical reports to be updated right away, not to be updated tomorrow after this overnight ETL process is done. So this creates, this creates a demand for these HTAP architectures and HTAP systems, and that's what we're trying to achieve at GridGain. So we're trying to, as I said before, to create a system that can handle different types of workloads with a single data set. So you have a single system, you have a single cluster of nodes that holds all your data, and you execute all different types of workloads on that cluster. So you execute operational transactional operations, operational like transactional workloads, updating and reading the data in real time. You execute ad hoc analytical queries on the same cluster. You do real-time machine learning and all that stuff in the single system. So there are many, applications and use cases where this can be useful. So this is just not by any means full list of our customers that we work with. Probably one of the biggest markets is financial services. These are like banks, financial institutions, things like that. But nowadays we have more and more customers and use cases in different other areas like logistics, telecommunications, healthcare, IoT, and many others. So how can we actually use that to accelerate the SQL without replacing the RDBMS? So to start the conversation about this, I would like to outline that Apache Ignite and GridGain is a pretty flexible system. So as I mentioned before, we have different options for persistence. You can integrate with third-party persistence, and you can use the native option, and you can work without persistence at all if that's what your use case requires or allows. So this essentially creates like 4 different memory modes. I would call them this way. Essentially, so the first one is you can use GridGain as a pure in-memory storage without any persistence. So that's very straightforward. All data is in memory. That's the best option from performance standpoint. Obviously, you will never get better performance than you have from pure in-memory solution. But that does not survive any cluster restart. So if cluster goes down for whatever reason, you lose your data, and then you have to get it from somewhere else. And sometimes it's not even possible. So then you can integrate with third-party database, and that's what I'm going to talk in more detail in the next several minutes. So this option is a good trade-off, between having good performance and essentially having a requirement to replace the database altogether. So you can still keep your database, but get better performance from the distributed memory system. And then finally, you have in memory, you have a native persistence option that kind of split in these two options, where you have a full data copy in memory or partial data copy in memory. And I will talk a little bit about this at the end of the presentation. All right, so how do we actually solve this problem of accelerating a SQL application? So there is actually a pretty typical solution to that. It's not a new problem, and there are many systems that can address this issue. And it's typically solved with what we call in-memory data grid systems. So any in-memory data grid essentially is a system, is an in-memory distributed key value store, like a distributed hash map, that slides between your database and the application, and makes sure that the data is in sync between the database and the key value storage. So pretty much any data grid would support read-through semantics, meaning that when you update something in the data grid, it's also updated in the database. When you read something and it's not in memory yet, it will be read from the database. So everything is great. So you don't have to replace the database. The database is still your source of truth. That's actually the place where you store the data. But you have certain operational data set, the most important data in the in-memory data grid, to provide better performance, to provide faster access. So all is great, but the only issue here is that essentially this is a key value store. This is a distributed hash map, and the main API for this kind of store is a key value API. So essentially, you are limited to primary key lookups. You cannot do arbitrary search. You cannot use SQL as you are used to, because you're migrating from a SQL database, right? And that's where GridGain comes into play, and Apache Ignite. So one of the biggest differentiator of Apache Ignite and GridGain in the data grid world is comprehensive SQL support. So on top of the key value store, so the procedure and the approach with Apache Ignite and GridGain would be actually the same. You will slide it in between the application and the database. You will configure the mappings between the Ignite schema and the database schema. Then you will load the data into memory, have it there in the memory for fast access. You will still have read-through and write-through. You actually can still use the key value APIs. So all that is supported, but on top of that, you also get distributed SQL support, which means that you can also execute any SQL queries and use SQL language to work with your data, which is a big advantage because, first of all, it's much more flexible. You can do any arbitrary search on your data. You can query by secondary indexes. You can query, you can do groupings, you can do aggregations and all that without any custom logic. You just execute SQL queries as you do that with the traditional database. And also, yeah, so yeah, I'm sorry. So essentially, this is much more flexible, and like this is something that you're used to, right? Because you are migrating from a relational database, so you do not have to completely migrate to some new API, to some new approaches in development of your application, and you essentially get, if not a zero code change in your application, but at least like a minimal code change, so you don't have to completely rework it. So the distributed SQL support in Ignite and GridGain essentially is based on our memory-centric storage, of course. So you have your data in your dynamically scaling cluster with both data and indexes stored in memory and with optional persistence on disk. And you have different connectivity options, and you have different SQL APIs. So in more detail, so these are the connectivity options that you have. So first of all, there are native APIs in different platforms. We support Java, .NET, and C++. So if you have like a Java application or .NET application, you can just create a Ignite client node there, embed it into the application, and execute SQL queries, and use all other APIs as well. So as I said, you can mix and match them. So you can use this client node within the application to execute different workloads from the application. But at the same time, if you want to work only with SQL, you can also use JDBC or ODBC drivers that are also provided out of the box. So you can essentially connect with any like JDBC tool, for example, and query GridGain cluster from that tool. So you don't even have to create a special application for that. ODBC driver is also very useful. Having ODBC driver basically means that you can connect from virtually any platform. You can connect from Python, from PHP, and other programming languages and other platforms. You can also integrate with different BI tools like Tableau, for example. So you simply inject the Ignite ODBC driver into Tableau, and Tableau will query the data in the cluster and show you those beautiful reports. So we have the data definition language. So essentially, you can create the tables and create the schemas using DDL, meaning that or change the schema as well. Like, for example, at some point you have your schema, everything works fine, but you want to add a column, for example, or you want to maybe add a new index on one of the columns to accelerate your query. So you can do that dynamically in the runtime using those DDL statements. And finally, the data manipulation language, of course, this is the biggest part. We have NC99 compliant SQL at the moment for select statements. So all the joins, order bys, group bys, different conditions, all that is supported, as well as subqueries. And we also have the ability to update the data using SQL as well. So you can use insert, update, delete statements to change data in your cluster, to update data in your cluster as well. Joins is a very important topic. This is something that we invested a lot of resources in to properly support joins. So we, of course, support collocated joins. So collocated join is essentially a join that is executed on the collocated data set. Collocated data set means that all the rows that are joined with each other are reside on the same node. Like, for example, if you have a city table and the country table, right? And the city table has country ID field, which references the country table as a foreign key, right? And then you do a join between those two tables. So you can tell that your data set is collocated if all cities that belong to the same country are stored on the same node, and the row that represents that country is also on that exact node, right? So you have the Canada on the node 1, for example, and all the Canadian cities grouped together on the same node. I'm not going to go into details how you can do that, but there are different ways in Ignite to achieve that. So it's not actually complicated. It's not difficult to do. So you can achieve that, and that's a recommended approach in the most cases, because that gives you the best performance. But the point is that it's not always possible. And many systems, they require you to collocate the data set if you do joins, which is, as I said, not always possible, especially for ad hoc analytical use cases. There are use cases where you cannot predict all the possible joins. There are also use cases where you technically cannot achieve collocation for all possible joins without, a lot of denormalization and duplication of the data. So this brings us to the topic of non-collocated joins, which are also supported by Apache Ignite and GridGain. So non-collocated join means that although data is not collocated, so you don't have all the Canadian cities on a single node, for example, join will still work, and it will still give you the correct result. However, that would essentially involve certain data reshuffling and data movement between the nodes. Basically, what would happen is that the SQL engine would make sure that data is collocated during the query execution. So it will reshuffle the data so that it's temporarily collocated and will execute the query on that temporarily collocated data set. This works, but that provides much worse performance. So this is something that might be used in rare cases when, as I said, you cannot predict some joins and you cannot technically achieve joins, but you still have rare queries that are maybe not so important for, from performance standpoint, but you still want to execute them. And that's where non-collocated joins come into play. So this is a useful feature, especially, as I said, for analytical hybrid workloads, where you would optimize your collocation strategy and optimize your performance as much as possible for the operational workloads. But for analytical workloads, you can sometimes sacrifice performance because of those issues. Yeah, so that's actually like an overview of what we can do with the with GridGain and how we can accelerate our SQL applications. And I want to show you like a quick demo of how you can actually do that in practice. And so let me go to the Web Console first. So Web Console is our monitoring tool that is provided by Apache Ignite and has also some additional capabilities in the version provided by GridGain. So it has multiple features. It has multiple screens, obviously. So we are currently on the configuration screen. Yeah. So first of all, I have my database. I have a Postgres server running on my laptop, and I have this world DB database. This is like a typical example database that comes from MySQL and that was migrated to all the known databases for this kind of examples and demos. So what we have here is we have like 3 tables. We have city table, we have country table, and country language table with different information about cities and countries. So if I do like select star from city, for example, I will get multiple cities with their populations, with the reference to their country through the country code field, and things like that. So I have this database, and imagine that we have an application that uses this database and runs certain SQL queries with all join subqueries and all that. So how would we accelerate this application? So let's go back to the Web Console. Web Console has this configuration screen. That's the first screen that you would often start with. It essentially allows you to create cluster configurations. So you can put all the properties, parameters for your cluster together on the UI, and then it will create like the configuration file, for example, things like that. But on top of that, it has one very important feature and a very powerful feature. So we have this import from database button here. So essentially, it will read our schema from our database and create all the configurations and all the boilerplate code for you, so that you can migrate with minimal effort. So here I just provide, JDBC driver jar, the JDBC driver name, the URL to my database, username and password, and Web Console connects to the database. Now we have the list of schemas here. We're actually interested only in the public schema, which has all those tables that we want to import. So you see it found all our 3 tables. And so we want all those 3 tables to be imported and essentially mirrored in our GridGain cluster. So let's click next here. These are some additional parameters. I will go with the defaults, maybe change the package name for our classes just to make it more beautiful. So I click save. So what happens is that it created my new cluster here that already has 3 caches and 3 models for our 3 tables. So essentially, it read the schema from the database and generated the configurations, generated the mappings for GridGain data schema. So if I go to this cluster, if I click on this imported cluster, first of all, I can change all different parameters here. Like, for example, I don't want to use multicast discovery. I will do just static IP with the local host because I'm going to run on my laptop only. So I have my 3 caches, city cache, country cache, and country language cache. They are all based on the information that Web Console got from the database. And now I click Save and Download. And what happens now is that it essentially saves all the settings that I just changed. And I also downloaded a zip file, which is essentially a project, like a POM-based, Maven-based project with all those configurations and the code that we need to start. So I can just open this project in my IDE. So it's in my downloads. So I just select this folder and open the folder. So let me show you what we have here, first of all. So first of all, we have the configurations generated for server node and for client node. Like, let's go to the server node, for example. So it has the data source configuration for our database. So it already knows how to connect to the database. There is some internal discovery configuration, which essentially is responsible, for nodes joining each other and knowing about each other. And then we have the cache configuration property, which is the biggest one. It has all the cache configurations with all the mappings between the database and the GridGain schema, with all the query fields, with all the indexes and things like that. So as you can tell, I mean, it's a pretty big configuration file, and I didn't have to create it manually. So it was all generated by the Web Console automatically for me, based on those 3 tables that I have in the database. The only thing I need to do is I need to provide my credentials and coordinates to the database. So I put the local host here instead of the host, 5432 for the port number, world DB for the database name, and then my username here, and the password is empty. So that's all I actually need to change here in terms of configuration. And then let's go to the code. So first of all, we have all our data model classes here, like city, for example, with all those fields that actually map to the fields in the table. So if you don't want to use SQL, for example, for some operations, or maybe for all operations, you can and you want to use key value APIs and work with objects. So you have all those objects also generated for you, so you don't have to write this code as well. Also, we have some startup classes here, which are basically just convenient, small classes that start up the nodes, server nodes or client nodes for us. So essentially, I will use the server node Spring startup class, for example, which simply starts an embedded node using this configuration file that I've just shown. So let's start this one to have a GridGain node up and running. Takes a second to compile. All right, so it's starting up. All right, so it's up and running. So it shows us that we have one server here. Everything is good. So now we have to load the data. So we have our node up, we have our cluster up and running, but it doesn't have any data yet. Data is in the database. So we want to have our data in memory. So for that, we go to the load package, and we have this load caches class here, which again is pretty simple. It just starts an Ignite client node embedded here in this process and loads all 3 caches. So there is a load cache method, which essentially does what we want. It would load all the data from the table into the in-memory cluster. So let me run this one to make sure we have the data in our server node. All right, so it's connected as a client. So we see that we have server 1, clients 1 here, and it loaded all 3 caches, and then it just exits. So if you go back to the server node, then we can actually see that we had this client joined here, and then it left, and now we actually have the data. So how do we check that we have the data? And for that, I will go back to the web console. And now I will actually go to the monitoring tab, and I will go to the dashboard. So this is just the monitoring component that shows multiple different metrics about what happens to the cluster. So starting with basics like CPU usage, heap usage, different throughput metrics like cache sizes. So we already see that cache sizes are not 0, so we have something here in the caches. And then if I scroll down, so first of all, I have my node here. So it is connected to this node that we just started. And we also have our caches. So this table here shows the list of our caches. So we see that we have the 3 caches that we are actually looking for: city cache, country cache, and country language cache. And all those caches, they have a certain amount of entries in them. All right, so now we have our cluster up and running, and we loaded the data from the database into our cluster. So now let's run some queries, right? So as I said, you can at this point you can use different APIs. You can use key value APIs. You can run compute. You can do different kind of things, and you can write your applications, that would use different APIs. But you also have the SQL support, which is something that I want to talk more about today. The SQL support, again, you can execute SQL queries, using your JDBC driver or RDBMS driver that we provide, or directly from the application. And you can also do that from the web console as well. So you don't even have to write a single line of code. So I already have like a notebook prepared here with some queries, just to demonstrate, what we can do. So first of all, like a simple query. Let's run a very simple query that just queries the name, essentially like the most populated countries, 10 most populated countries. So we will select the name of the country, the population of the country from the country table, and we will order by population, and we will limit the result set by 10 records. So let's execute this one. So that's the result set. This already is taken from the in-memory cluster. So we did not go to the database for this data. We have everything in memory, and we read this data from memory from a highly scalable cluster. So the performance is going to be much better, and the scalability, which is even more important, would be much better. So if you have like millions of these kind of queries executed in parallel, you can scale your system out to make sure that the system can handle this kind of load. So yeah, the most populated country is China, then we have India, then US, and so on. So yeah, so it sounds about right. So let's look at a bit more complicated query. This one is essentially, this one has a join between the city table and the country table using this country code field. So what we have here is we essentially query the countries with the biggest average population of the city, right? So we aggregate by the city population, we calculate average, country, and then we order by this average population. And we also filter out these 3 countries which we are interested in right now using the where clause. So let's execute this one. So again, everything works as expected. We have results for our 3 countries, USA, Russia, and China. We have results for these 3 countries, and we have like an average population, average city population for every country here, and it's ordered by this field. So again, the result looks correct. China has the biggest average city population, then we have Russia, then we have United States. All right, so these are select queries, but as I mentioned earlier, we also can do updates using SQL as well. So let's check what is the population of Netherlands, first of all, right? So it has like 15-something million people there. And let's go to the database and execute like the same query. So I will do select population from country, where name equals Netherlands, right? So same result, almost 16 million people live in Netherlands. Now let's imagine we want to update this, right? So we want to change this population to some other value, or like 30 million, for example. So, you know, like a typical update statement, as usual, as it looks like an update statement as in any other database. So we do update country, set population to the new value, where name is Netherlands. So let's update this one. So update is successful. So now query, if we do the previous query, which selects the population for Netherlands, it will give us new value. And now, so one of the purposes of any memory data grid system, which includes GridGain and Ignite, is to make sure that the memory cluster is in sync with the database. So essentially, what happens in this case is that when we update the in-memory store, it will write through into the database, and we should have the new value in the database here, which we actually do. So we now have the new value for the population of the Netherlands in both the memory cluster and database. So if you lose the cluster, right, for whatever reason, you still have your data in the database, and it's in sync with what you did earlier, right? It's in sync with all the updates you did earlier, so you don't lose the consistency as well. Although you are actually doing it through the in-memory layer. So yeah, the whole point here is that as you probably noticed, I didn't have to write a single line of code. So I started, you know, with just a database in the Postgres, and in 10 minutes I converted it into a GridGain cluster that has the data and that can be used to run the queries, and I can still use SQL to work with the data. So you, as I already mentioned several times, you don't have to switch to any other APIs. You don't have to rework your application to work with some other APIs and completely change how it is implemented. So obviously, I mean, you will probably have to do some changes in the code. You will have to think about collocation because it's a distributed system if you have a lot of joins and things like that. So it's not like a completely transparent switch from one system to another. But the fact that you have SQL support makes this effort minimal. So it reduces the effort as much as possible. All right, and so finally, just briefly, I want to talk about what you can do as a next step, right? So, like imagine you have, you know, you have your database and you have your GridGain and memory layer sitting in between the database and the application. So you now have the scalability for SQL query execution. You now have the, and you still have the consistency of the database. But the database here is still a bottleneck, regardless of all the advantages that are provided by in-memory layer. So first of all, updates. Updates is the biggest concern here. So if you want to make sure that the database and the in-memory layer is in full sync at any point of time, you have to make sure you have to do the update synchronously. So essentially what happens is that when you update the in-memory layer, you synchronously update the database. So performance and scalability for updates doesn't change much in this case. So this is kind of, this is good for use cases that have a lot of reads, but not that much writes. But if you have a lot of writes, then probably performance and scalability won't change much, right? It's still, it is still a bottleneck. Another challenge is that when you lose the cluster with this approach, with this architecture, you lose all the data that is in memory, and you cannot query, you cannot do SQL queries anymore, because if you do arbitrary search, you cannot actually go into the database. There's no way to know what to query from the database. That essentially means that every time you restart the cluster, you have to reload the data, and reloading the data for for large data sets can take quite a bit of time, and that might be a huge concern from the availability standpoint. So essentially, if you lose your cluster, you have like a power outage, for example, you then need like several hours, for example, to reload the data into memory to make it available to the applications again. This is obviously not always acceptable. Yeah, so these are the main challenges here. Yeah, and also the third challenge, yeah, it's kind of related to the previous one, is that the fact that you need to have all the data in memory. You need to you cannot really have like a subset of data in memory and a superset of data on disk. So you have to load all the data that might be required for your queries into the memory, even if though it's not like very frequently used. So these are challenges around this approach, and to overcome this challenge, we created our native persistence option. Native persistence option is essentially like a distributed disk store. So every node will have its own portion of the data locally on its own local disk, right? So it is distributed now in the same way as the in-memory layer is distributed, which means that it's not a bottleneck anymore. It's also a scalable storage on disk level as well, and also it's highly integrated with the in-memory store, which essentially means that Ignite can read the data both from memory and from disk transparently for the application. So now the application doesn't really care about whether the data is in memory or not. Even if all the data is on disk, Ignite will be able to query it, regardless of which API you use. So this overcomes the other two challenges, and introduces what we call instantaneous restarts. So you can essentially, if you restart the cluster, you don't have to reload anything. You have everything on disk. Performance will probably go down a little bit because of the fact that everything is on disk and nothing is in memory, but data will be available right away. All you need to do is restart the nodes, restart the processes, and there is no need for rehydration. And also this allows you to have like a bigger data set on disk and a smaller data set in memory, which is again is very important for HTAP, for hybrid workloads, because typical situation is that you have smaller operational data set that you want to have in memory at all times for faster access, faster processing, and then you have like a huge historical data set that can go like years in the past. And it would be very expensive to have all this in memory, and it's not even reasonable to have all this in memory. You don't really need that. You don't need like a lightning fast performance for these queries. You're okay if they run for several seconds. So in this case, you can configure Ignite to have a superset of data on disk. It always have the superset of data on disk, but have only partial data set in memory. And that brings us to these two different options, memory modes that you can use when the native persistence is used. So the native persistence and all this, like the whole architecture is based on this durable memory architecture. That's how we call it. So durable memory architecture is essentially a page memory-based architecture. So all the data is split in multiple pages, and every page can be stored either in memory or on disk. So this is essentially like this is very similar to what we have in operational systems, for example, like Linux. All the operational systems, they use that for swapping, right? So when they run out of memory, they start to use disk instead of RAM, and they put the pages on disk. In our case, we use it for persistence, so we always have everything on disk, and we can have a subset of data in memory. But architecture is very similar to what you have in the operating system. And finally, that how it looks like, from a single node perspective. So essentially, what happens is that whenever you update something in RAM, it is also persisted in the write-ahead log. Write-ahead log is the append-only file. So essentially, it is, and it is a local file because we have a distributed storage. So it's a pretty fast operation. So it happens synchronously. So you synchronously update the disk here, but you don't have any random access here. You don't go through the network or anything like that. This is just an append operation to the local file, which is fairly fast, especially on good modern like SSDs. And once we wrote into the write-ahead log, we can acknowledge the operation to the client, saying that update is successful in both memory and disk. And then there is the checkpointing process, which is just a background process, and it will write what we call dirty pages, the pages that are not persisted yet, into the partition files. And essentially, every node would have a subset of those partition files. Like if you have 1,000 partitions, for example, and 5 nodes, every node would have around 200 of those files for different partition. So that's just how it looks like from the from the architecture and from the workflow perspective. Yeah. So to summarize all that, so essentially, GridGain is a platform, is a flexible platform that you can use for different type of workloads, including transactional workloads and analytical workloads. And you can even mix and match those workloads into the single system. You can use GridGain as a data grid, as any data grid, sliding it in between the database and the application, but at the same time taking advantage of the SQL support so that you do not have to rewrite your applications completely. And as a step further, you can also use the native persistence option to overcome all the bottlenecks and all the issues of the third-party databases. But that's probably something that you want to do down the road. So using it as a data grid in conjunction with a third-party database can be a good first step, with switching to a native persistence option as a next step in the future. So that's all I have. Thank you everyone for listening, and I'm ready to answer any questions. Alisa, I'll hand it over to you.
Okay, thank you very much, Val. So if you have any questions for Val, go ahead and enter them in the questions field within the GoToWebinar control panel, and I'll read them as they come in. So Val, the first question is, what do I need to do if I add a database column later?
So if you add your database column later, you can use the DDL to alter the table in the. So there are actually like two different aspects there. So the first one is like the storage level. So if you use key value APIs, for example, we support dynamic schema through what we call binary object API. So you can go to the documentation and read more about this. It's called binary object. Binary object is essentially API that allows you to work with the objects without deserializing them into classes. So instead of using like POJ, if you expect this kind of a dynamic change, you can use those binary object APIs instead of using POJ classes, and they are like dynamic by nature. So you don't have to do anything essentially. So if you add a new column, then you just you have to reload this column somehow. That probably would require some additional logic to fetch this data from the database, new data from the database, but then you just use this binary object API. On the SQL level, pretty much the same, but you need to modify the SQL schema with the DDL statement. So you just use the alter table command to modify that.
Okay, great. So the next question is, there is a delay on row insert visibility, but how much is the delay?
Can you come again? Sorry, visibility of.
It says, if there is a delay on row insert visibility, how much is the delay?
So if it's, so there are two options. First of all, synchronous and asynchronous. So if you insert something into the data grid, by default it's synchronous. So when the update in the in-memory layer is completed, that actually means that that database is also updated. So that's fully synchronous. You can also use write behind option. In this case, it's asynchronous. Which would mean that the update on the memory layer would return control to the client before the database is actually updated. We'll just put it into a queue, and it will be eventually flushed into the database. Specific delay is hard to predict. It would depend on the configuration and the amount of updates that you have and on the network and many other things, many other factors. But essentially, the idea is that you use database for consistency. So once you switch to this kind of architecture, you use data grid APIs to integrate with interact with the data. So you do not actually access the database directly. So you don't even care much about the visibility from this point of view. But all we need to do is to make sure that all the updates are propagated to the database so that we do not lose them in case of any failure scenarios.
Okay, we've got a lot of questions here. So here's the next one. During schema extraction, is stored procedure extraction supported?
No. So stored procedures are actually, so we don't have stored procedures like direct stored procedures support, but you can always create use the compute engine for that, but that would require some some development, some coding, because it's Java based or .NET based or whatever platform you use. It's not SQL based.
Okay. Does GridGain plan to support graph database operations?
So I mean, GridGain is a pretty low-level database. So yeah, we don't have any specific support for graph operations, and I don't think we have any plans. But I don't know. I know a couple of customers who actually built something graph-like on top of GridGain, because it's essentially a pretty flexible system that can address many different use cases, and even those graph-like use cases can also be sometimes a good fit for GridGain.
Okay, next question. How smart is H2 SQL engine compared with my original database?
I mean, it has its own limitations, but I mean, first of all, it's highly customized, so it's not exactly the H2 engine that you would have if you just use the H2 database. So we did a lot of customizations there, and we replaced a lot of pluggable components that H2 has there. I mean, yeah, so there are things that it has certain limitations, but even if you hit those limitations, we have different ways to overcome this. So you can control the join order, for example. You can use hints. Overall, I mean, overall it's pretty smart, and I cannot say I see a lot of issues with that. But sometimes additional optimizations are required for different reasons. Sometimes it's due to the nature that the system is distributed. Sometimes due to some specifics of the H2 engine. But there are ways to overcome this.
Okay, we have time for a couple more questions. So the next one is, what about views that use link tables in SQL Server? How does GridGain and Ignite handle it during schema extraction and query execution?
So views, again, views is something that is not supported right now. Frankly, don't know if there are any plans or not in the community for this. So I believe you can extract view as a table essentially. So the web console and the cluster will treat the view as a regular table, and the load data from that view, essentially, like doing a select star from that view along with loading the table. But on the GridGain level, it's going to be a table. It's not going to be a view of multiple tables.
Okay. Let's see here. Ignite supports transactions with NoSQL API. Do they span several caches?
Yes, they do. They span several caches, several nodes, so it's a full distributed transactional support.
Okay, great. And then the final question is, what is the core difference between native Apache Ignite and GridGain Enterprise version?
So so the main difference is, so first of all, we have several features built on top of Ignite that we provide as a part of Enterprise Edition. As I mentioned, these are like data center replication. I have this on this slide. So data center replication, data snapshots and recovery. This is like essentially, you can take a full backup of the data and then recover. Security capabilities, monitoring capabilities, and things like that. So all the core functionalities in Apache Ignite, like pretty much everything that I was talking about, like everything that I was talking about is in Apache, is a part of Apache Ignite. But if you have a mission critical system with high availability requirements, that's where you might find our enterprise features useful. And also we have, we provide support, we provide professional services and things like that for the Apache Ignite and for the Enterprise Edition, of course.
Okay, well, that brings us to the top of the hour. Val, thank you for a great webinar. The audience was very engaged, large audience today. Thank you everyone for attending, and we hope to see you on a future show. And with that said, again, Val, thanks so much.
Thank you. Thank you, Alyssa. Thank you, everyone, for listening.